The next thing that we want to discuss are the gas laws. So when we're considering a gas sample, we need to take multiple pieces of information about that gas into consideration. First is going to be the temperature that the gas is at, because the temperature is going to change how fast the molecules are moving. We also have to take the amount into consideration. So how much of that gas there is. How many individual particles? This could also be individual particles. Because that will affect the pressure of the gas. Are they hitting each other? If there's a lot of them, are they not hitting each other because there isn't a lot of them? Finally, we have to take into account both the pressure of the gas, okay, what's the pressure that it's at, as well as the volume of the container. So the pressure and the volume, this is specifically of the container, and the pressure of the gas. Those will all affect our gas sample overall. If one of those 4 variables is changed, the other variables will be affected. The relationship between those variables, so temperature, amount, pressure, and volume, when they are changed, are called the gas laws. Early scientists explored these relationships between the variables of gases, and they came up with this idea of an ideal gas, which is a hypothetical construct of real gases under certain conditions. They found that many gases around us act very similarly. There are some exceptions to that assumption, but for the most part, most gases act very similar to each other. So for what we are going to be discussing in this course, we are only going to be worrying about ideal gases. Okay, everything that we're discussing is for gases that are ideal and act in an ideal manner. We won't discuss real gases in any way. You'll learn that in a future semester of chemistry. So I want to, before we start talking about the gas laws, I want to just bring in the idea of standard conditions. So the whole thing with the gas laws is that they show us how the quantity of gas and the number of moles for a given volume of gas will change with pressure and temperature. So it's how all of these variables relate to each other. So chemists have set up a set of numbers to compare those variables to. So we have this thing called standard temperature and pressure, also known as STP. So if a gas is at STP, it is at standard temperature and pressure. So the standard temperature is 273.15 Kelvin, which is also 0 degrees Celsius, if we remember back to our Kelvin conversions, okay? To convert from degrees Celsius to Kelvin, we take Kelvin, we take our degrees Celsius value and we add 273.15 to get Kelvin. So 273.15 Kelvin is 0 degrees Celsius. And the standard pressure is what we discussed before as being 1 atm or 101.3 kilopascals. We can also have an ideal volume at standard temperature and pressure. This is only for our ideal gases. Okay, so at STP, an ideal gas will have a volume of 22.4 liters, which is also referred to as standard molar volume. Okay, we'll need to know this STP expression, both for the problems that we're doing today in this lesson, as well as in your homework, because you may be told a gas is at STP, and you'll need to know that STP stands for a certain temperature and pressure so that you can solve the problem. So let's look at our gas laws. The first one is called Boyle's law. Boyle's law relates volume and pressure. And it says that if you increase the pressure on a system, this causes the volume to decrease. Also, decreasing the pressure on a system causes the volume to increase. So, the volume of a given amount of gas held at constant temperature is inversely proportional. I'm going to highlight that. Inversely proportional to the pressure under which it is measured. So pressure and volume are inversely related to each other. So in order to explore Boyle's law, we have to keep some of our variables constant. So if we want to understand the relationship between pressure and volume here, we have to keep temperature and amount, which we're going to show as N, because N stands for moles and amount is a mole. So we're going to keep temperature and number of moles constant. So we're really just relating P and V. Now, if we're changing the pressure and we want to see how it affects the volume, or if we're changing the volume and we want to see how it affects the pressure, we can use the relationship of P1 V1 equals P2 V2 to find how those variables will change when we change either the pressure or the volume. So this is very similar to our dilution equation, M1 V1 equals M2 V2. We're going to know 3 of those variables and determine the 4th. So let's practice this, because the best way to learn these types of concepts is through practice. So a methane sample occupying a volume of 2.15 liters at a pressure of 5.25 atm is allowed to expand at constant temperature until its pressure reaches 1.85 atms. Calculate the final volume. So we want to see how the volume changes when I decrease the pressure. Well, if I decrease the pressure, I would expect the volume to increase. So let's determine exactly what that volume is. So we're going to use our equation P1 V1 equals P2 V2, and we want to define all of our variables. So P1 V1, P2 V2. Well, we're looking for the final volume, so we need to determine or calculate V2. So now we want to define our other variables. Well, it says that we start with, or it occupies a volume of 2.5 liters at a pressure of 5.25 atm. So 2.5 liters and 5.25 atm are linked together. They need to go with each other, so that would make them our initial values for pressure and volume. So we have a volume of 2.15 liters and a pressure of 5.25 atm. The problem then says the gas is allowed to expand at constant temperature until its pressure reaches 1.85 atm. So that's our final pressure. And now we want to calculate the volume. Before we go into calculating that, I'll make a note about our units. For pressure, as we know, we have multiple units of pressure that we can utilize, but as long as the pressure of P1 and P2 are the same, you can use any pressure unit. If they're given in the problem as the same unit, then you can use them as is. If they're given as different units, then you may have to convert one to the other. And you get to choose what pressure unit you convert it to, okay? Because as long as they're the same, then the equivalency will be the same. It'll work out the same way. The same goes for volume. If you're given volumes in milliliters, as long as the volumes are in the same unit, then they work out the same way. Okay? So just keep that in mind as you're going through these problems. You don't need to do any extra pressure conversions unless the pressures are given to you in different pressure units. So now we can just plug things in. P1, 5.25 atm, times V1, 2.15 liters, is equal to P2, 1.85 atm, times the volume, which we don't know, of V2. So we're just going to do a little bit of algebra here. 5.25 times 2.15. To isolate V2, we'll divide both sides by 1.85 atm. So I'll divide that 11.28 by 1.85, and we get out that V2 is equal to 6.10. Now let's look at our units. ATMs, when I do this side of my equation, okay, when I divide, ATM is going to cancel. So again, if the pressure units are the same, they'll end up canceling. Our volume unit is in liters, which is the only unit left over. So our final volume here is in units of liters. If the problem asks for that unit in liters, then you're fine with your answer as is. If you're asked to convert then to milliliters or another volume unit, then you would do that after you've gotten the final volume. Then you can do your conversions from there. So just keep an eye on what units you're asked for in the problem when you're doing these in your homework and your exams. Let's do another one. If a 4.0 liter container of helium gas has a pressure of 10 atm, what pressure does the gas exert if the volume is increased to 6.0 liters? Okay, well, if we're increasing our volume, we should be decreasing our pressure based off of Boyle's law, P1V1 equals P2V2 down here. So we'll set up our variables, P1, V1, P2, V2. Well, we're looking for our final pressure, so we'll define that as P2. So now we just have to define P1, V1, and V2. So a 4.0 liter container has a pressure of 10 atm, and it was increased to a volume of 6. So the increased volume is our final volume, 6.0 liters, meaning that the 4.0 liters is our initial volume, which goes with the 4 liter container has a pressure of 10 atm. So 10 atm is our initial pressure. Okay, so we can then plug everything in. Our volume units are the same, so we can use them as is. We don't need to do any additional conversions. So P1 is 10.0 atms times V1 of 4.0 liters is equal to P2, which we're solving for, times V2 of 6.0 liters. So we'll divide both sides by 6 liters to isolate P2, and we get 10 times 4.0 divided by 6.0. We get a value of P2 of 6.7, I think, with sig figs. Yeah, let's call it 6.7 with sig figs. And if we look at our units, well, liters and liters cancel, so the only unit we're left with is atm. So this has units of atm. If a problem doesn't specify what units it wants it in, you can just keep it as is. You don't need to convert. Okay, so since this one said what pressure does the gas exert, well, we're assuming that we're measuring it in the same way as we did before the expansion, so the pressure unit would be measured in the same way with the same unit. Let's do an example from your ALEKS homework. This one I pulled specifically because of how we're asked to define the value for volume in this problem. So, a gas storage cylinder is in an ordinary chemical laboratory measures 2.1 centimeters wide and 8.4 centimeters high, and this is the label on it. Contents, nitrogen gas, pressure, 14.2 atm. If the cylinder is opened and the gas allowed to escape into a large empty plastic bag, what will the final volume of nitrogen gas, including what's collected in the plastic bag and what's left over in the container? Write your answers in liters. be sure your answer has the correct number of significant figures. So, for this problem, we want to find V2. So we need to define P1, V1, P2, V2. Well, our P1 is defined for us on our label here. That's 14.2 atm. For P2, this problem states that the gas is in an ordinary chemical lab and that it's allowed to escape into that lab. So if we're escaping into a normal room, okay, that would be standard temperature and pressure. So ordinary chemical lab is at standard temperature and pressure. So our standard pressure is 1 atm. This is where we need to know STP, and sometimes thinking about what STP means. If we're just at normal, if we're in a room, if the gas is in a room, then it's just going to be STP, and they may not state it in words. They may just say that the gas is in a room. We need to know that a gas in a normal room where we have no other information is at STP. Okay, so we're finding volume of 2. We now have to find our volume 1. Well, we're not given a volume directly in this problem. However, what we are given are the dimensions of the container the gas is in. And one of the properties of gases is that it takes the volume of the container that it's in. So if we know information about the container, we can find the container's volume. If we know the container's volume, then we know the gas's volume. Okay, so we know that the gas storage is in a cylinder, and we know the dimensions of that cylinder. So, is there a way that we can use a cylinder, its diameter, and its height to find a volume? Well, how do we normally find the volume of a cylinder? Volume of a cylinder is equal to pi r squared times the height. And if you're ever confused about what volume equation to use, depending on if it's a cylinder, a cube, a sphere, Alex does provide you with those equations in the data tab, so make sure you're looking for those there. So the volume of the cylinder is pi r squared times the height. Well, we're given that it's 21 centimeters wide, the entire cylinder, so this would be the diameter, and it's 8.4 centimeters high, so that would be the height. So we know h, we almost know r, we have the diameter, so we need to take 2.1 centimeters and divide that by 2 to get the radius, and that equals 1.05 centimeters for the radius. So once we have the radius and the height of our cylinder, we could just plug this into our volume equation. So this would be equal to pi times r, the radius, 1.05 centimeters squared, times the height, which is 8.4 centimeters. So we'll take that into our calculator. We'll do pi. I'm using the symbol pi. You could also type in 3.14. Either works. I'm going to multiply that by 1.05 squared and multiply that by the height, 8.4. And I get a volume of 29.09. Now we need to determine what our units are. So when we're doing our math here, we're seeing that we take 1.05 centimeters and we're squaring it. So that would give us units that are in centimeters squared, because that square not only applies to the number, it also applies to the unit that is on that number as well. So 1.05 centimeters squared is equal to a unit of centimeters squared. We're then multiplying that by the height, which is also in units of centimeters. So if I take centimeters squared and multiply it by centimeters again, I get units of centimeters cubed, which, if we recall from our previous lessons, centimeters cubed is a volume unit. And it has a direct relationship to a liter volume. we know that 1 centimeter cubed is equal to 1 milliliter. Right? We remember that back from one of our earlier chapters when we were talking about derived units and how to use conversions. So 1 centimeter cubed is equal to 1 milliliter. So 29.09 centimeters cubed is still a volume, has volume units, but since our question is asking us to put an answer in liters, we need to have this volume in liter units. So centimeters cubed turns into milliliters. Now that we have milliliters, we're going to want to convert that to liters so that we're in our proper units for our final answer. So we'll take that value and we'll divide it by 1,000 because there are 1,000 milliliters in 1 liter. So 29.09 divided by 1,000 is equal to 0.02909 liters. So we had to do a little bit of extra work to find our initial volume, and that's why I wanted to bring this ALEKS homework here, just in case you're given this problem where you need to find the volume using dimensions such as these for diameter and height. So there are multiple ways to find volume, especially of a container. So now that we have these values for P1 and P2 and V2 or V1, we can solve for V2, just plugging everything in like we did previously. So we're going to take 14.2 ATM and we're going to multiply that by our volume. And that's going to be equal to our P2, which is 1 ATM, and allows us to solve for V2. Well, we know dividing by 1 isn't going to do anything, so we just need to take 14.2 multiplied by 0.02909. If you don't believe me that dividing by 1 doesn't do anything, it's the same number. Okay, so we get V2 is equal to 0.413 liters and then with significant figures, this would simplify to 0.41 liters. It's 2 sig figs due to your diameter and height variables up there at the top. Okay, so that was Boyle's law. Our next gas law is called Amundsen's law, where we relate pressure and temperature. So Amundsen's law says that as a container is cooled, the gas gets colder and the pressure decreases. It also states that as a container is heated, the gas gets warmer and the pressure increases. And in these cases, our volume and our temperature, our volume and our moles are remaining constant. So we're only looking at how pressure and temperature change and affect each other. So when we're comparing two samples, we have pressure divided by temperature as our relationship. Okay, these are directly related. So when we're comparing two samples, we have P1 divided by T1, and that's going to be equal to P2 divided by T2. So when we're indirectly related or inversely related, like Boyle's law, we have them multiplied together. And when we have them directly related, we have division of those two variables. So we can see here in this image that we have a gas and it's at low pressure, and as we start to heat it, okay, we're heating this, we're going from a hot plate on medium to a hot plate on high, we see that as we increase the temperature, we're also increasing the pressure. A great example of this that we see in our daily lives is our tire pressure. Sometimes you'll notice that as we go between seasons, maybe between fall and winter or winter and spring, our tire pressure lights come on during those times of year. And that's because of our difference in temperature. As it gets colder at night when we're going from fall to winter, the pressure or the gas that's in our tires will start to get colder as well, and that therefore decreases the overall pressure in your tires. The same thing happens as we go from winter to spring, because as it starts to warm up, the gas will also start to warm up and the pressure will increase. Okay, this one is directly talking about how fast the molecules are moving. They get colder, they move slower, the pressure decreases. And as it gets warmer, the molecules move faster and therefore they increase their pressure. So let's look at a problem with this. Okay, we're going to set this up very similar to how we did in our previous examples, but we now are going to use a different equation. P1 over T1 equals P2 over T2. Now I will make a very important note that temperature must be in Kelvin. It must be in Kelvin for doing all of these problems. The temperature may be measured in degrees Celsius, but we cannot use degrees Celsius for these problems, even if it's the same unit on either side. Okay, we have to use the Kelvin unit for our temperature for these problems. So here we have the problem of assume the pressure in the tires of your car is 33.5 psi at 20.8 degrees Celsius. What is the pressure when the gas in your tires heats up to 43.3 degrees Celsius? So we're heating up the pressure or the gas in our tires, and we want to see how our pressure changes. Well, as we increase the temperature, we should see an increase in the pressure because they are directly related. So to start this problem, we'll define our variables just like we did previously. P1, now we have T1, P2, T2. So our initial pressure is 33.5 psi. Our initial temperature is 20.8 degrees Celsius. We're finding our final pressure, we don't know that yet, but we do have our final temperature of 43.3 degrees Celsius. Now we can't use the temperatures as they are given. We cannot use degrees Celsius for these problems. Even though both temperatures are in degrees Celsius, we must convert them to Kelvin. Okay, so what we're going to have to do first is add 273.15 to get both of these values into Kelvin. So I'm just using my Kelvin conversion that I have here. Kelvin equals degrees Celsius plus 273.15. So we have for our first temperature 293.95 Kelvin, and for our second 316.45 Kelvin. So now that we have our temperatures in Kelvin, now we can solve the problem. So we'll take P1, 33.5 psi, divide it by T1, 293.95 Kelvin, and we'll set that equal to P2, which we don't know, divided by T2, 316.45. Now you can solve this problem a couple of different ways. You can either just do basic algebra where you simplify both sides, then multiply and divide to solve for x, or you can cross multiply and then solve for x that way. Both ways will work. So what I'm going to do is do 33.5 divided by 293.95. So that simplifies this side of my equation. And then I'm going to multiply both sides by 316.45 to solve for P2. There we go. 1139.65. So we get a P2 that is equal to 36.1. Helps if I write all the numbers. 36.1 psi. So 3 sig figs on there. So that's our pressure after the gas in our tire has been heated. Now, if you wanted to prove this to yourself, you can go through this problem again without converting to Celsius. You can just skip that step, or without converting to Kelvin, just skip that step. And you can see that you would not get that pressure out if you did not convert to Kelvin. So we have to convert to Kelvin when we're using temperature in all of our gas problems. Okay, so just make sure you're not skipping that step and converting your temperature to Kelvin. Okay, so we get 36.1 for our pressure. For our next problem, I want you to do the same thing. Assume the pressure in the tires of your car is 33.5 psi at 20.8 degrees Celsius. Now I want you to find the temperature when the gas in your tires cools down. So that should say cools down to 5 degrees Celsius. So instead of heating it up, we're cooling it down. So you're going to set up the problem in a similar way. Okay, our P1 and T1 are staying the same. You just need to change T2. So pause your video and try to solve for the P2 in this problem. We know P1, that's equal to 33.5 psi. And we know T1, already in Kelvin, that's 293.95 Kelvin. We're solving for P2. So our T2 is the only one that we have to change here. So we have 5 degrees Celsius, which we need to convert to Kelvin by adding 273.15. And we get out 278.15 Kelvin. So we're going to set up the problem in the same way. We have 33.5 psi divided by that 293.95 is equal to P2 over T2, which is 278.15 Kelvin. So again, you can solve this problem in a couple different ways. You can cross multiply, or you can simplify it and solve for x. So I'm going to do 33.5 divided by 293.15, and then I'm going to multiply both sides by 278.15 in order to solve for P2. So we get a P2 of 31.8 psi with 3 sig figs. So we can see that our pressure decreased when we decreased our volume, or our temperature, I should say. Okay, our next gas law is Charles' law, where we relate volume and temperature. So the volume of a given amount of gas is directly proportional, we'll highlight that, directly proportional to its temperature when pressure and moles are held constant. So here we're only varying volume and temperature, so we're keeping pressure and number of moles constant. So we see that as the temperature increases, the volume also increases, and as the temperature decreases, the volume will decrease. So our relationship between volume and temperature is V over T here. And if we're ever comparing two samples, we take V1 over T1 is equal to V2 over T2. Okay, these are directly related, so their relationship is through division. So as we increase our temperature, we're going to also increase our volume. So let's practice this. It's going to be very similar to the examples we did previously. Under constant pressure conditions, a sample of hydrogen gas, initially at 88 degrees Celsius and 9.8 liters, is cooled until its final volume is 3.4 liters. What's its final temperature? Well, we're going to start this off the same way. V1, T1, V2, T2. We know V1, it's 9.8 liters. And we know T1, it's 88 degrees Celsius. We know the final volume is 3.4 liters. We want to find the final temperature. So the first thing we have to do before we plug things in is convert our temperature to Kelvin. So we get 88 plus 273.15, and that's 361.15 Kelvin. So when we solve for T2 here, its units are automatically going to be in Kelvin. You don't need to do an additional conversion because liters will end up canceling and you'll be left with units of Kelvin. Okay, so we then just plug everything in and solve for T2. So we'll take V1 over T1 is equal So we'll take V1, 9.8 liters, over T1, 361.15 Kelvin, is equal to V2, 3.4 liters, divided by T2, which we're solving for. The math to find the answer is a little bit different than before. Again, you can cross multiply and solve for x, or you can simplify both sides and then solve for x. Either way is fine. I personally like simplifying and then solving for x, so I'll take 9.8, divide that by my temperature, 361.15. Nope, that's not the right one. 9.8 divided by 361.15. That don't make too much of a difference, but so we get this simplifies to 0.02630, and that's equal to 3.4 divided by T2. If I want to solve for T2, I'm going to multiply both sides by T2, and then divide both sides by 0.02630. So we end up getting that T2 is equal to 3.4 liters divided by 0.02630. And that's going to be liters over Kelvin, technically. So we then take 3.4 and we divide that by 0.02630, and we get a final temperature of T2 to be 129.277 Kelvin. And with sig figs, that comes out to 130 Kelvin. And with sig figs, let's be not ambiguous. 1.3 times 10 to the second Kelvin. So we decreased our volume, therefore we decreased our temperature. And we got our temperature already in units of Kelvin. We don't have to do any other conversions. Now, if I asked for the final temperature in degrees Celsius, we'd then have to convert from Kelvin to Celsius. But just keep an eye out on what units you're looking for. I always find that the math at this point, like solving for T2 here when it's like this, always confuses students. So just make sure you're rearranging your numbers correctly. If you're always getting the wrong answer when you're doing these types of problems, I suggest rearranging this equation first to solve for the variable that you need, and then plug in your numbers, rather than plugging in your numbers and then trying to solve for a variable. Sometimes having the numbers in there makes it confusing, so if you can follow your variables without the numbers and rearrange it that way and then plug things in, that becomes a lot easier. So instead you could do multiply both sides by T2, you would end up then getting T2 times V1 over T1 is equal to V2. So then you can multiply both sides by T1 over V1. So you end up getting T2 is equal to V2 times T1 over V1. So it's just doing some algebra to solve. And then once you have it rearranged to solve for the variable that you want, then you can plug in your numbers and solve that way. Or you can cross multiply, solve for x. You can simplify and solve for x. Again, there's multiple ways that you can solve these types of problems. Okay, let's try a couple more. And I want you to try these ones independently. So I'll put our equation back up at the top. V1 over T1 is equal to V2 over T2. So there's our equation. So I want you to try these two problems on your own. A balloon that contains 0.5 liters of air at 25 degrees Celsius is cooled to negative 196 degrees Celsius. What volume does the balloon now occupy? In the second problem, at a volume of 0.5 liters of air at 37 degrees Celsius is expelled from the lungs into cold surroundings at 0 degrees Celsius. What volume in liters does the expelled air occupy at this temperature? So pause your video and try these two problems using our equation V1 over T1 equals V2 over T2 for Charles' law. The first thing that you want to do in each of these problems is to convert your temperatures to Kelvin. That's always the first thing you want to do, is make sure your temperatures are in Kelvin. So we know V1 is 0.50 liters. T1 is 25. We're going to make that into Kelvin by adding 273.15. So that's 298.15 Kelvin. And that's equal to V2, which we currently don't know, over T2. So we get negative 196. Negative 196 plus 273.15 is 77.15 Kelvin. So now we just solve for V2. We're going to take 0.5 divided by 298.15 and then multiply both sides by 77.15. And that gets us a V2 of 0.12938 liters. And with sig figs, let's see, we're looking at 2 sig figs here, 0.13 liters for V2. So I decreased my temperature, therefore I decreased my volume. Next up, we have 0.5 liters as our V1, and our T1 is 37 plus 273.15. So that's 310.15 Kelvin. That's going to be equal to V2, which we're looking for, and T2, which is 0 degrees Celsius, also 273.15 Kelvin. So we'll solve for V2, 0.5 divided by 310.15. And we multiply both sides by 273.15 to get a final volume V2 of 0.44 liters with sig figs. Next, I want to do a problem from our ALEKS homework. An Arctic weather balloon is filled with 1.52 liters of helium gas inside a prep shed. The volume inside the shed is 13 degrees Celsius. The balloon is then taken outside where the temperature is negative 10 degrees Celsius. Calculate the new volume of the balloon. Assume the pressure of the balloon stays constant at exactly 1 atm. Be sure your answer has the correct number of significant figures. So this is very similar to our last two problems. So what I want you to do is pause the video and try this problem on your own. Again, the first thing you're going to want to do to start this problem is to convert your temperatures to Kelvin. So we know V1 is 1.52 liters, and T1 is 13 degrees Celsius, so we'll add 273.15 to convert that to Kelvin. 286.15 Kelvin. That's going to be equal to V2, which we're solving for, and T2 is negative 10 degrees Celsius, which again will add 273.152 to get our temperature in Kelvin. So we get 263.15 Kelvin. And now we just solve 1.52 divided by 286.15, which is then multiplied by 263.15. So we get a volume of 1.3978 liters, and this would have two significant figures of 1.4 liters. So we again see that as we decrease our temperature, we decrease our volume following Charles' law. Our next law is relating the amount of gas and the volume of that gas. And here, when we're talking about the amount of gas, we're talking about the moles. So this is called Avogadro's law, where volume and number of moles are directly proportional. So for a confined gas, the volume and number of moles are directly proportional if the pressure and temperature both remain constant. Equal volumes of all gases measured under the same temperature and pressure contain the same number of molecules. So again, because this is a direct proportional law where volume and moles are directly proportional, they're related through division. So volume divided by moles, V over N. When we're comparing two samples, we do V1 over N1 is equal to V2 over N2, which is Avogadro's law. Before we jump into practice problems of Avogadro's law, with Avogadro's law, because the volume of the gas is directly proportional to the number of moles, a balanced equation of gases can be compared by the ratio of volumes instead of the ratio of moles. So when we were talking about solutions in our previous lessons, we always use mole-to-mole ratios to go between one substance and another. With volumes, with gases, if we're going between gases directly, this does not work if we're going between liquids and gases or solids and gases. It's only between two gases. So if we have a reaction just like this, where we take hydrogen gas, react it with nitrogen gas to get ammonium gas out, if we can compare not only via mole-to-mole ratios, but now via volume-to-volume ratios because of Avogadro's law. So we see here that 3 molecules of hydrogen gas combine with 1 molecule of nitrogen gas and produce 2 molecules of ammonia gas. We can also say the same thing goes for moles. 3 moles of hydrogen combines with 1 mole of nitrogen to get out 2 moles of ammonia. Now with Avogadro's law, where moles and volumes are directly proportional, 3 volumes of hydrogen gas combine with 1 volume of nitrogen gas to create 2 volumes of ammonia gas. So we can go from molecules to moles to volumes with our balanced equation. We'll find this useful when we start doing stoichiometry problems in our next lesson. So let's practice with Avogadro's law, where V1 over N1 equals V2 over N2. A 6.0 liter sample at constant temperature and pressure contains 0.5 moles of gas. If an additional 0.25 moles of gas at the same pressure and temperature are added to the container, what is the final total volume of the gas? Okay, so we have V1, N1, V2, N2. So we know our initial volume of 6.0 liters. That was given to us in the problem. And at that volume, we have 0.5 moles of this gas. We're finding the final total volume, so we're looking for V2. We now need to determine N2. It says we add in 0.25 moles to our already existing 0.5 moles. So N2, so we're increasing our number of moles of gas. So we're going to take that 0.5 moles that we start with and add the 0.25 moles to it. So we get out that N2 is actually 0.75 moles. So we've increased our number of moles, therefore we should be increasing our volume. So let's do that. V1 is 6 liters and N1 is 0.5 moles. V2 is what we're solving for, and N2 is 0.75 moles to reflect the addition of 0.25 moles to our initial container. So we take 6.0 and divide that by 0.5, and then we multiply that by 0.75. So our final volume, V2, is equal to 9.0 liters. So we can see that as we increased our number of moles, we therefore increased our volume. Our next problem comes from our ALEKS homework, where molecular chlorine and molecular fluorine combine to form a gaseous product. Under the same conditions of temperature and pressure, it is found that 1 volume of Cl2 reacts with 3 volumes of F2 to yield 2 volumes of the product. We want to know what is the formula of the product. So, when we're reading volumes, we should also read that as moles. So the 1 volume, that's our stoichiometric coefficient, 1 mole. So we say 1 volume of chlorine, Cl2, reacts with 3 volumes of F2, which can also be seen as 3 moles. And we get out 2 volumes of our product, which for right now I'm going to call X. So again, we're relating volumes and moles. Volumes is equal to moles. So now we want to determine the formula of the product. Well, we have to take balancing into account. If I have Cl and I have F, well, on my reactant side, I have 2 chlorines and I have 6 fluorines. This equation, as I've written it, is already balanced because I've already used my molar coefficients to do the proper balancing, right? We reacted in balanced stoichiometric quantities in this problem. So my reactant side should also have 2 chlorines and 6 fluorines. So X is going to somehow be related to Cl and F. Okay, we're looking for that formula of X. And I know that there's 2 of them on my product side because of the 2 here that was given in the problem. Well, writing ClF as is already got me my 2 chlorines. However, I'm short by 4 fluorines. So we can basically see this 2 and this 6 as if we divide by our stoichiometric coefficient, I should have each X should have 1 chlorine and 3 fluorines. Well, each of these both have 1 chlorine in them already, so I just need 3 fluorines in there as well. So our balanced formula is Cl2 plus 3F2 turns into 2ClF3, which is balanced on both sides. I have 2 chlorines and 6 fluorines on both sides. And it still says that 1 volume of chlorine gas reacts with 3 volumes of fluorine gas to create 2 volumes of product, chlorine trifluoride. So the formula of the product is ClF3, chlorine trifluoride. So we're using our knowledge of balanced equations, and now our new knowledge of that volumes can be equal to moles using Avogadro's law in order to balance an equation and find the product. The last law that we will talk about in today's lesson is the combined gas law. The combined gas law can be used to solve problems where any or all of our 4 variables are changed. So our initial combined gas law is P1 V1 over N1 T1 equals P2 V2 over N2 T2. This combines all of those relationships between pressure, volume, temperature, and number of moles, right? Let's see, here, P1 and V1, P2 and V2, that one is Boyle's law. P over T, that's Amundsen's law. Then we have V over T, that's Charles' law. And then we have V over N, that's Avogadro's law. So this combines all of the laws together, which is why it's called the combined gas law. We've combined all of them together. Now, typically in a combined gas law problem, we have a fixed amount of gas. So we have a fixed amount of gas here. Therefore, the value of moles would be the same on either side, or we can see it as being held constant. Right, so N and N would be the same on either side, so they can essentially cancel out. So this cancels out the variable of N in our first equation, and it reduces down to P1 V1 over T1 is equal to P2 V2 over T2. Now this is very similar to our previous equations because when we're given these types of problems, we'll know 5 of the 6 variables, we'll know how different variables were changed, and then we can solve for the 6th variable that we're looking for. So let's do that. A sample of ammonia is found to occupy 0.250 liters under laboratory conditions of 27 degrees Celsius and 0.85 atm. Find the volume of this sample at 0 degrees Celsius and 1 atm. So here in this problem, we're changing both the temperature and the pressure. We want to find how the volume would then be affected by those 2 changes. So we have P1, B1, T1, and P2, V2, T2. So we start with a volume of 0.250 liters, a temperature of 27 degrees Celsius, and a pressure of 0.85 atm. We say that our final temperature is going to be 0 degrees Celsius, and our final pressure is going to be 1 atm. We now want to find V2. So the first thing we're going to do is convert these temperatures from Celsius to Kelvin. So we'll take 27 and that will give us 300.15 Kelvin, and 0 degrees Celsius is just 273.15 Kelvin. And now we can plug everything in. So P1 is 0.85 times V1, which is 0.25, divided by T1 of 300.15. We then get that equal to P2, which is 1, times V2, which we don't know, times T2, 273. Okay, so now it just comes down to doing some algebra here. We're going to do 0.850 times 0.250 divided by 300.15. So we get out 0.0007079. That's equal to 1 times V2 divided by 273. So we'll multiply that value by 273.15. So we get V2 is equal to 0.193 liters. So just solving there. So we saw that as we decreased the temperature and increased the pressure, we saw a decrease in our volume. So it's relating how all of those different laws come together and how the different variables affect each other. Okay, let's try another. A given sample of gas has a volume of 4.20 liters at 60 degrees Celsius, my degree signs disappeared, and 1 atm of pressure. Calculate its pressure if the volume is changed to 5 liters and the temperature is changed to 27 degrees Celsius. So pause your video and try this problem. Here we're given everything we need, we just have to convert our temperatures to Kelvin. So we have P1 of 1 atm, V1 of 4.20 liters, divided by T1, which is 60 plus 273, so 333.15 Kelvin. And that's going to be equal to P2, which we're solving for, times 5 liters, which is our V2, divided by our T2, which is 27, which we will add 273.15, so 300.15 Kelvin. Okay, now it just comes down to some algebra. We have 1 times 4.2 divided by 333.15. We get 0.012607, and that equals, we could do 5.0 divided by 300.5. We get P2 times 0.016658, and then we just take 0.012607 and divide that by 0.016658. to get P2 of 0.757 atm. Our initial pressure was an atm, so our final pressure will be an atm. Now, with 6 variables, the algebra for these types of problems can get tricky. So again, I encourage you to both practice with me and practice independently, and if you keep getting the wrong answer for these types of problems, it's probably coming down to an algebra error. So I would suggest rearranging your variables first before plugging things in. So for this problem, if we wanted to isolate P2, we would multiply both sides by T2 over V2. So that would get P2 is equal to T2 times P1 times V1 over V2 times T1. Okay, so rearrange your variables first, get the equation, and then plug in your values in order to then just solve automatically. Okay, our last problem for this lesson says a weather balloon contains 222 liters of helium at 20 degrees Celsius and 760 millimeters of mercury. What is the volume of the balloon when it ascends to an altitude where the temperature is -40 degrees Celsius and the pressure is 540 millimeters of mercury? Okay, so here we're looking for the volume of the balloon. We're given our initial pressure, volume, and temperature, and we're given our final pressure and our final volume. So we're going to use P1 V1 over T1 is equal to P2 V2 over T2. So try this last combined law problem on your own. So pause your video and try this one independently. For this problem, let's show the rearrangement first and then plugging it in. Let's try it that way. So we have P1 V1 over T1, P2 V2 over T2. So if we want to solve for V2, in order to do that, we're going to multiply both sides by T2 over P2 so that they cancel out. So I would put T2 over P2 on this side, so I get that V2 is equal to T2 times P1 times V1 divided by P2 times T1. So now we could just plug in all of our known values. T2 is -40 degrees Celsius, so we'll take -40, add 273.15 to it. We get 233.15 Kelvin times P1, which is 760 millimeters of Hg. I'll not use units for space. Times V1 of 222 liters. That's this guy right there. Divided by P2, which is 540 millimeters of mercury, times T1, which is 20 degrees Celsius. So 20 plus 273.15 gets 293.15. So now that we've rearranged, we just have to plug this into our calculators. So I'm going to use my parentheses just to make sure I'm multiplying and dividing by the correct things. I'm going to take 233.15 times 760 times 222, close parentheses, divide by 540 times 293.15. So I get a V2 of 248.15 0.495 liters. With sig figs, let's say that's 2, so 250 liters. With non-ambiguity, 2.5 times 10 to the 2 liters, so we don't have an ambiguous 0 there at the end. Okay, so we have covered both pressure units and conversions, as well as all of our gas laws and the relationship between pressure, volume, temperature, and number of moles of gas. So we can use this to now practice with our ALEKS homework and practice all of the algebra that has to go on with these types of problems.